Welcome back to Infos Math Solutions, where we don't just learn DSA, we learn how to think like a programmer. Imagine you open Instagram, a celebrity posts a photo. Within a few seconds, 10 million people comment on it. Now, suppose Instagram wants to show a newly pinned comment at the top, let's say here. What should it do? Should it move every single existing comment one position below, like this? That sounds ridiculous, doesn't it? Now let's think about another app, let's say Amazon. Suppose you're scrolling through thousands of products like this, and suddenly a new sponsored product needs to be appear near the top, or maybe here we want to show it. Then will Amazon shift every product in memory just to insert one new item? Probably not. So here's today's question. If arrays are so powerful, why did computer scientists invent another data structure called a linked list? By the end of this video, you won't just know what a linked list is, you will understand why it exists, where it's useful, and how interviewers expect you to think. So let's begin. Before learning something new, let's first understand the problem. Because every data structure in computer science was invented to solve a problem, not because someone wanted to make students suffer before exams. Let's revisit arrays. Suppose we have an array, let's say int, and the name of the array is AR, and its element be 10, 20, 30, 40, and 50. Now let's just make it here like how it looks in the memory. So 10, then this is 20, 30, 40, and this one is 50. Now here's something important. These elements are stored next to each other in memory. Imagine the memory addresses. Like if we say for the first one it's 1000, then for the second one it will be 1004. For the third one it will be 1008. For the fourth one it will be 1012 and 1016 for the fifth one. So, did you notice something? Every element sits continuously. That's why arrays are incredibly fast. If I ask you what is the fourth element, the computer directly jumps to it. No searching, no traveling, just one calculation. That's why accessing an element is big O of 1. Amazing, but everything has a price. What happens if we want to insert a new element? Suppose we want 25. So 25 should be inserted here, and that is what we want. So for that, what we have to do is we have to six elements now in the array. So we'll be needing a new space. So we'll create a new space in the memory, and in this we'll make six blocks or like this. Now we'll see the elements. So first it was 10, 20, now 25 to be inserted here. Then this is 30, this one is 40, and this one is 50. And we can delete the one we made here. So now we got a new array where this 25 is inserted. But for that, what we had to do, we have to create a new memory. We have to delete the old one. And before that, we had to copy these elements. Imagine doing this not for five numbers, but for 50 million users or 50 millions of Instagram comments or YouTube live chat. That would be extremely expensive. So here's the first limitation of arrays. Insertion in the middle requires shifting elements. Another problem, arrays usually have a fixed size. Let's say we create an array of size 100. For that, I'll write int ARR and here 100. Now suddenly we need to store 101 elements. Now what? You can't magically stretch the array. Often the program needs to create a larger array, copy everything, delete the old one, then continue. Again, lots of unnecessary work. So now we have two important problems. First is frequent insertion is costly, and second is fixed size can become a limitation. So naturally, computer scientists ask, can we store data differently? Instead of keeping everything side by side, can every piece of data simply know where the next piece is? And that question led to one of the most important data structures, which is linked list. So, what is the main idea? Forget coding for a minute. Let's think visually. Imagine we are playing a treasure hunt. You find the first clue. That clue doesn't tell you the entire route, it only tells you go to the next location. Let's draw it here. So, first, let's say that we have one location here and we have one clue. And in the queue, we have the location for the next place. So we went to the next location, which is our L2, and here again we have one more clue, which we are naming as C2. So now this tells the location for the third position. So let's say we went here, then this is location 3, and again it gives clue to the next location like this. Then we can go to the next location and so on. So each clue only knows where the next clue is. That's exactly how a linked list works. Every node stores two things. First is data, and the second is the location for the next node. The first part stores the actual value, and the second part stores the address of the next node. Notice something interesting. The nodes need to be next to each other? No, it's not like that. So the nodes don't need to be next to each other, they can live anywhere in memory. That's completely okay. Like we saw here in this. First node was this, second was this, and third was present here. So the each node just knows where the next node is present. Think of it like Google Maps. Your current location doesn't need to be physically close to the next city in memory. You simply have the route to reach it. Treasure hunt clues help us understand the idea of moving from one node to the next, but unlike paper clues, computers use memory addresses, not written directions. So the analogy helps build intuition, but the actual implementation uses pointers. So now that we understand the idea, let's build our first node in CPP. So first we will include IO stream, then we'll write using namespace std here inside the node class. So we have made one class named as node, then we'll write public and then we'll write int data. So this stores the actual information, this data variable, and it is of the integer type as we have made it. It could be 10, 20, don't even anything. Now the next thing is node star next. So this is the heart of a linked list. It does not store another node, it stores the address of another node. That's why it's a pointer. Finally, we'll make the constructor here. So it will be node int value and then we'll write data is equal to value and next is equal to null pointer. So when a node is first created, it does not point to any another node. So we initialize it with null pointer, which means there is no next node. If we understand it using a diagram, then suppose we have this node, we have created this node and we'll have the value for data. For example, we say 10. So we have this data 10. And now we don't know where is the next node. Maybe this one or anywhere in the memory. So we simply just write here null because we don't know the position right now. Now we'll create main class. So int main, and inside this we'll initialize a node star first is equal to new node, and let's say 10. 10 means we are giving the value of the data as 10. The keyword new creates the node in heap memory. Think of the heap as a large storage area where objects can live until we delete them. First itself is just a pointer stored in your program. It holds the address of that node in the heap. So if we just say here, then first is basically first is here. Let me just remove this. And it points to this node. It just stores the address of this node. So far, we learned why linked lists were invented. Arrays were fast for accessing elements, but inserting an element in the middle meant shifting many elements. Then we learned that a linked list stores data differently. Instead of storing everything together in memory, every node simply remembers where the next node is. Now let's actually build one from scratch. So here we had just written node star first is equal to new node 10. Now let's just make a complete linked list. So for that we make another one, so which is node star second is equal to new node 20, and then we'll say first next is equal to second. What it means is like, so this is the first node, this is the second node. We give it 10 and we give this as 20. So this is what written in the first and second line of code here. Now it says first next is second. So this thing which stores the address of the next node, this, it refers to second. And what is second? Second is the address of this node. So basically we are assigning the value or the address of this node here in the next. Basically what will happen is this one is second and this is first. So in the next node, in this the address of this one will be stored, and so we can easily reach out to the second node using the first node. If for example the memory address of this is 2000, then this may be 5000. It doesn't matter, it can be stored anywhere in the memory. So it is not at all like arrays where the nodes had to be stored next to each other. Now let's make another node. Let's say here node star third is equal to new node 30. and we'll connect this node. And how we'll connect it? Let's see here. So we have created another node, node 3, and in this we gave the value as 30. Now here in this we'll tell or we store the address of this node, which is node third. So that's why we wrote second. Second means second node. Then arrow next, which means this portion. In this, its value will be equal to the address of the third node. Now we have created our linked list. Now here's something important. Suppose tomorrow you forgot where the first node is. Can you still access the linked list? Think for a second. The answer is no. If nobody remembers the address of the first node, the entire linked list becomes unreachable. That's why we keep a spatial pointer called head. Think of it as the entry gate. Once you know the first node, you can reach every other node. So if you lose the head, you lose everything. You lose the access to the linked list. That's why protecting the head pointer is extremely important. Now suppose I ask you to print every element. How will you do it? Can we directly jump to the last node? No. Unlike arrays, linked lists don't support random access. We have to travel one node at a time. So let's say like we are having this node 1, node 2, and here we have the node 3. This is our head because this is the first node. And we have to print all the elements like here it's 10, this one is 20, this one is 30. So what we will do, we'll first go to head, then we'll print the value written here in its data, and then we'll see the next of the first node. So this will give the address of the second node. Then in the second node, we'll print the value written in data, and then we'll go to the next. The next will give us the address of the third node, and similarly we'll print 30 and then we'll see next. If this here inside this will get a null, then it means that linked list is over and we only had 3 nodes. So let's write the code. So we'll make a temporary node first, node star temp is equal to first. Then we'll write while temp is not equal to null because we know when we'll get a null, it means it's the end of the linked list. And then we'll print temp data and temp is equal to temp next. Let's run this and we got 10, 20, 30, which is the right answer. So let's try run it once. Initially temp is equal to first, so temp points here and then it says that temp is not equal to null, so it's equal to first, it is not null, then it will print 10. Then next is temp is equal to temp next, so it temp will get the address which is stored here, so it went to second node, then it print 20, then it went to second node, and so on like this. So if you notice something that we never changed the original head pointer. We created a temporary pointer called temp. This is considered good practice because the head pointer remains safe. So far we have built a linked list from scratch, connected nodes together and learned how to traverse it safely. But one question still remains. Is traversal fast or slow? How does its performance compare with arrays? And where are linked lists actually used in software that millions of people use every day? Let's answer those questions next. So first is accessing an element. Suppose I ask you print the third node. Can we directly jump to it? No. Let's see why. Because we here we have first we have the address of the head, then we have the address of the second node stored here. Here we have the address of the third node. So before going to the first and second node, we cannot directly go to the third node. So we cannot skip any node before reaching the last one we want, because every node only knows the address of the next node. If there are n nodes, in the worst case, we may visit all n nodes. So then the time complexity becomes big O of n. So now if we compare it with arrays, and if we say here, example our array is 10, 20, 30, 40, then the index will be 0, 1, 2, 3. If I ask for index 2, the computer immediately just reach here. No traveling, no visiting previous elements. That's why array have an time complexity big O of 1 to access the element. Now suppose we have to print every element. So we must visit 10, then 20, then 30, then 40. If there are n nodes, we perform n visits. So we'll have a time complexity of big O of n in linked list as well as in arrays. At this point, you might be thinking arrays are faster, so why would anyone use linked list? That's a fantastic question. Remember the problem we discussed at the beginning, insertion. Let's imagine two situations like we already did, which is we have the array 10, 20, 30, 40, 50, and you want to insert 25 here. So it was a big problem if it had 1 million elements, because we had to shift almost 1 million elements if it was an array. That's expensive. So if you want to do it in linked list, then don't have to move every node. We simply change a few links. Only the connections change. The existing nodes stay exactly where they are. That's the beauty of a linked list. We'll learn exactly how this works in the next video. For now, just remember the idea. One question students often ask is, do companies usually use linked list? Yes, but maybe not in the obvious places you expect. Let's look at a few examples. Suppose I open Google. Here I open YouTube. Then you can see we got this. Now let's say we have to go back. Then you can simply use this back and this forward. The- For this, the browser needs to remember where you came from. So internally, browsers often manage this navigation using linked structures or closely related structures, because each page naturally connects to previous and next pages. The important idea isn't that every browser literally stores history as a simple linked list. The implementation can be more complex, but linked relationships are a natural way to model navigation. We can also talk about Spotify, like we are listening to a song, song A, then we go to song B, then we go to song C. So when song A finishes, it simply moves to this one, When song B finishes, it simply goes to song C. So the idea of each item pointing to another item is similar to how linked lists work. If we talk about undo, then you can see if I press Ctrl Z, then it is removed. If I press Ctrl Y, then you can see it is redo. So the application needs to remember a sequence of actions and move between them efficiently. Many editors use linked structures or related data structures internally to manage this history. Now, a question. If I need to access the 500th element thousands of times every second, should we use a linked list? Think first. To reach the 500 node, what we have to do? First, we have to visit the first node, then it tells the address for the second node, then second will for third node, and so on like this. So to reach 500, we have to visit every node. So that's slow. So in this case, an array is much better here because random access is big O of 1. So in this case, linked list is not the right choice. So whenever you're solving a coding problem, ask yourself these questions. Does the data size change frequently? Are insertions and deletions frequent? Is random access not important? Is sequential traversal acceptable? If your answer is yes to most of these, then a linked list might be a good choice. So that's it for today's video. I hope linked lists feel a lot less intimidating now. And remember, today's goal wasn't to learn every linked list operation. Today's goal was to build a strong foundation. Because once your foundation is clear, the upcoming operations will make much more sense. In the next video, we'll answer a very interesting question. How do we insert a new node at the beginning, at the end, or anywhere in the middle without shifting all the other nodes? Once you understand that, you will finally see why linked lists were invented in the first place. If you found this video helpful, don't forget to like the video and subscribe to it for smart solutions so you don't miss the next part of this DSA series. Until then, happy coding and I'll see you in the next one.